The present paper discusses an end-to-end deep learning model in order to assist in land cover classification through hyperspectral imaging. Hyperspectral imaging, like other spectral imaging, collects and processes information from across the electromagnetic spectrum. The goal of hyperspectral imaging is to obtain the spectrum for each pixel in the image of a scene, with the purpose of finding objects, identifying materials, or detecting processes. Hyperspectral imaging produces a three-dimensional data volumes corresponding to the x, y, and lambda, where x and y give the spatial location of the pixel and lambda corresponds to the spectral dimension. The present paper is to use data obtained through hyperspectral imaging on obtaining the type of land cover for each pixel in the image. Most of the significant prior work in the domain is based on pixel-wise classification, where we give a class or here a land cover type to each pixel of the image. Previous approaches include modified KNN algorithm, where Euclidean distances are used to predict classes in the input space or a transformed space. This, however, generalized poorly in case of inadequate data. Support vector machines based models were used, which followed a two-step approach which included dimensionality reduction to tackle high values of spectral dimensions and lack of training data. These reductions were not data-driven and thus led to suboptimal feature selection. Other methods also included Gaussian mixture model, relevance vector machines, etc. There are three primary problems surrounding the hyperspectral image classification. First, the curse of dimensionality. As hyperspectral images can have hundreds or even thousands of bands, the number of samples or training pixels required in order to maintain statistical confidence and functionality grows exponentially with the increase in narrow bands. Also, a great number of dimensions result in a high number of classes to be achieved. So where it is in fact natural to have HSI classification for complex land cover, the need of a huge amount of training data creates a significant problem. This, combined with the scarcity of labeled training data, results in Hughes phenomenon. Another problem includes spatial variability of spectral information. Efficient modeling of spectral spatial context is necessary to address the problem, and recently, deep learning neural networks have shown to be capable of such context modeling. The deep learning methodologies can be broadly classified into two different categories. First follows a two-step procedure: dimensionality reduction, followed by spectral spatial learning using autoencoders. Autoencoders are artificial neural networks that reconstruct the input vector at the output with the minimum distortion, which gives the output as a dimensionally reduced version of the input that often encodes other useful semantic operation. This is followed by multi-class logistic regression. The problem here lies in the fact that feature learning is not task specific and thus results in suboptimal results. Second category of methods uses convolution neural network for feature learning and classification in an end-to-end fashion. CNN uses extensive parameter sharing in order to tackle the curse of dimensionality. Earlier proposed architecture include learning abstract spectral signatures in a hierarchical fashion, which did not consider the spatial context, or an end-to-end CNN architecture for spectral spatial feature learning and classification using pixel pair features in order to compensate for the data scarcity. However, no prior model has tackled all the three problems mentioned before. In the present model, a deep neural network architecture is proposed that learns band-specific spectral spatial features. The model gives the second best performance on the leaderboard without any dataset augmentation. The architecture aims to tackle all the three prior mentioned problems. It consists of three cascaded blocks. Block 1 takes P cross NC input volume, where NC are the number of spectral channels and P cross P are the number of pixels, and performs preliminary feature transformation on the spectral axis. It splits the channel into bands and provides it as the input to block 2, where parallel neural networks are used to extract low and mid-level spectral spatial features. The features or activation maps obtained are then concatenated and fed into block 3.